All right. Hello again. Okay, let's start this. Okay. Okay, so we're going to go through um, the slideshow here, and we're just going to do eyes right now. We're going to start on eyes because eyes and ears is a lot of material to cover at once, um, which you probably just want to split it up to begin with. But it's all in chapter 17. So you can follow along through your book, take notes while we go through this if you need to. But we're going to start with the eye and start our slideshow here. Dun, dun, dun. All right, so we got special senses, eyes and ears. Okay, so we already went over eyes a little bit in lab. So we'll go through some of the structures pretty quickly, and then we'll go through. We didn't mention anything about how the neurology actually works for how you see. So we'll go through that, and then once we get to the end of the eye, we will stop, and then I'll record another one for the ear. Okay. So the accessory structures of the eye are the ones that provide protection. So the external structures here. So we have the eyelid. This is the skin around the eye. Okay, and then we have the palpable fissure, which is this space in between the eyelids. Okay, or the palpebra. Okay, the medial angle and the lateral angle, they are obviously on the medial side and lateral side. So that's where the eyelids connect here, lateral canthus and medial canthus on this side. Okay, eyelashes. Okay, those are the robust hair cells here. Tarsal gland. Tarsal glands are sebaceous glands that are on the inner margin of the eyelid, and they release a lipid-rich secretion so that the eyelids don't stick together. Okay, so you can blink and they're not going to stick. The lacrimal caruncle, okay, that is in the middle here near the medial canthus. This has glands in it that produce a thick secretion. So this is like that hard, crusty, like sleep stuff in your eyes when you wake up and you got to rub it out. That's produced by this lacrimal caruncle. Okay. Then two conditions here: inflammation of the tarsal gland causes a cyst called the chalazion, and then the stye is an infection of the sebaceous glands associated with the eyelash. So the stye is actually localized swelling and pain. So mainly when we have pain there, it's usually a stye. Okay. Moving deeper, we got the muscles around the eye, orbicularis oculi. Okay, this is that circular muscle around the eye and helps to close the eyelid. The levator palpebra superioris is the one that helps to raise the upper eyelid. Okay, open your eyelid. Then we have the conjunctiva, which is deeper than that. That is the epithelial covering of the inner surface of the eyelids and the outer surface of the eyeball. Okay, so we have the palpebral conjunctiva, which is the inner surface of the eyelids, and then that is continuous with the bulbar conjunctiva, which covers the anterior surface of the eye. Okay, so the bulbar conjunctiva then is continuous with the cornea, which is the transparent part of the eye made out of fibrous layer, 5 to 7 layers thick. Okay, so that's this clear part. So when we have conjunctivitis, that is redness. Normally you notice around the eye here, where it's inflammation from physical, allergic, chemical irritation of this conjunctiva. Okay. Now we're going to go over the lacrimal apparatus. Okay, this is where we have we produce tears, we distribute them across the eyeball, and then remove the tears into the nasolacrimal duct. Okay, so the superior lateral side of the eye is where the lacrimal duct, where the lacrimal gland is. Okay, this produces the tears, and then those tears run through the lacrimal ducts across the surface of the eye into the lacrimal lake. Okay, whoops, touching my mouse here. Into the lacrimal lake. The lacrimal lake is here on the medial canthus. Okay, this covers the lacrimal caruncle. once the tears get here, they go through two little holes called the lacrimal puncta, okay, through the canaliculi here into the nasolacrimal or the lacrimal sac. Okay. Once it's in the lacrimal sac, then it starts to drain inferior into the nasolacrimal duct, and then that opens inferior to the inferior nasal conchae. Okay. So that's how tears are produced and how they are distributed and then removed. Okay. So you're familiar with that mechanism and where all those little parts are. Okay. So now we'll go through the layers of the eyeball. Okay, we talked about this in lab the other day before spring break. This was 3 layers of the eyeball. Okay, we have outer fibrous layer, the intermediate vascular layer, and then the deeper retinal layer. Okay, so we'll start on the outer surface. We have the sclera. The sclera is that white part. It contains collagen and elastic fibers. Okay, this is where all the muscles actually attach into that move the eyeball. Okay, superior rectus, inferior rectus, lateral medial rectus, superior oblique, inferior oblique, all those attach into the sclera of the eyeball. Okay. It contains small blood vessels, and then we are continuous with the cornea. Okay, the cornea is continuous with the sclera. You can see here, here's the white part that goes around the eye, okay, and then it goes in continuous with this cornea here. The difference with that is that the cornea is multiple layers of collagen, but there's no blood flow. Okay, there's no blood vessels there, but there are a lot of nerve endings, so it's the most sensitive portion of the eye also. Okay, so we don't want blood vessels where we need to have light and images coming through. Okay, then we just see a bunch of lines across our face. So there's no blood vessels in there. There's blood vessels in the sclera. All right, so the next deeper layer is an intermediate vascular layer. Okay, so this starts with the iris. Okay, and we have the iris, which is the pigmented flattened ring containing blood vessels. Okay, that is here. Okay, so that's the deeper one in that picture. It's the iris. The 2 layers of smooth pupillary muscles. We have an image down here that shows us, okay, there's one muscle that constricts the pupil and one that dilates the pupil. Okay, there's not one muscle that constricts and tightens and then relaxes to dilate. One muscle constricts, one muscle contracts to constrict it, and one muscle contracts to dilate. Okay, so we have the pupillary constrictor, which is the inner one here, and then the pupillary dilator, which is the outer one here. Okay, so one of these muscles has to activate to either dilate or constrict. Okay. Okay, so that's the iris and how that works. Then the pupil is in the center, which is the opening through the iris. Okay, we have the ciliary bodies. Ciliary bodies are here. Okay, so these thickened portions, they have the ciliary muscles, and then they project ciliary processes here. These are also called ciliary zonules or suspensory ligaments. Okay, I usually say suspensory ligaments, but whatever you want to say is fine. Okay, so the ciliary body has muscles, ciliary muscles, and it projects these suspensory ligaments, which help shape the lens. And so they attach to the lens and help shape the lens. And we'll talk more about that in a little bit. The choroid. The choroid is posterior to that. Okay, that starts after the choroida serrata. Okay, we have this middle portion here, reddish, I guess, through here. All right, so that's the choroid vascular layer. It separates the fibrous layer of the inner layer, and it's posterior to the aorta serrata. And it's covered by the sclera and attaches to the outermost layer of the retina. All right, so next we'll look at the retinal layer, which is inside here. Okay, we went from outside to inside. So we have the deeper layer, or the retinal layer. We have we have thin pigmented layer, and then we have a thicker neural layer. Okay, so we talked about this a little bit in lab. We need the pigmented layer to absorb the light that passes through the neural layer. If we didn't absorb this, we'd have light kind of bouncing around the eye, and we'll get multiple different images, and we wouldn't be able to process it very well. Okay, so we need that pigmented layer to absorb the light passing through the neural layer to prevent visual echoes. And then we have the thicker neural layer, which is deeper. Okay, so we have the sclera here, okay, and then we have, this shows some of the vascular layer. I guess it's black part. The black part's the pigmented. This doesn't good. Okay, the white part is the sclera here on the outside. This yellow part here is the choroid and the ciliary body, so that's the vascular layer. And then we have the two layers here. This red part here is the neural layer. Okay, so that's deeper into the eye, the neural layer. And then we have the pigmented layer right outside of that, okay, that black part. And so when the light comes through the eye, it comes through the lens, comes here, goes through the neural layer, and absorbs into the pigmented layer. Okay, sorry. So with the neural layer, the thick neural layer, we have rods, cones. Rods are sensitive to light, okay, and the cones are color sensitive. They help with color vision and sharpness and clarity of the image. And then we have intrinsically photosensitive retinal ganglion cells. Okay, these respond to different brightnesses to help the body with its circadian rhythms. Okay. So those are all photoreceptors within the neural layer. And then in the eye, this image is also for the cavities. Okay, so we have a posterior cavity, anterior cavity. And the anterior cavity is broken up into an anterior chamber, which is in front of the iris, a posterior chamber, which is behind the iris. And then we have that posterior cavity here. And so the anterior chamber is filled with clear watery fluid. So remember in lab, when we kind of cut through the cow eye, we had that watery stuff that came out. That was the aqueous humor from the anterior cavity. Okay? And then that jelly kind of stuff in the posterior side of the eye, that was the vitreous body made up of the vitreous humor. Okay, so it's like jelly. All right, so this, we'll talk about the aqueous humor and the vitreous body in a minute. Okay, so here's a good one. This is in your book. Shows all the layers of the eye, all the different parts of the eye. This is good to to help learn all the spots of the eye. Okay, but this one we're going to talk about the macula and the fovea. Okay, we can see here that the eye is tilted a bit, so when the light comes through, it goes straight back onto a particular portion of the eye in the neural layer. Okay, the macula is the region of the retina where there are no rods, but there's high concentration of cones. Okay, so this is and the fovea is the highest concentration. So we have in here the macula, which is kind of a broader area where there's just cones. Okay, high concentration of just cones here, and then the highest concentration is like one little spot, which is the fovea. Okay, and that's where we need to bring our focus. Okay, so the lens kind of changes shape to bring focus, focal point, right on the fovea, so we can see stuff clearly. When it comes in front of or behind, then the image starts to turn out blurry. And we'll look at that in a second. Okay. All right, so this is the organization of the neural layer and the pigmented layer here. Okay, so we have the pigments here, pigmented layer here, pigmented layer on the top. Okay, and then we have the neural layer. Okay, so we see the rods, which kind of look like rods, and the cones, which have a little cone at the end. Okay, rods and cones. Okay, those all are attached close to the pigmented layer here. And then those synapse with bipolar cells. And these bipolar cells then synapse with a ganglion cell. And we have two different cells, the horizontal cell and the amacrine cell. And these can help facilitate or inhibit communication between the photoreceptors and the ganglion. So it alters the sensitivity of the retina. Okay. So light comes through this way, comes back, so it's going to the top, absorbs into the pigment layer, Okay, and we're going to talk in a second about how the photons coming through stimulate the rods and the cones and how that activates the bipolar cells and ganglion. Okay. All right, here's where we have optic disc. So this is where our blind spot is. All right, so the optic disc here is just where the optic nerve is. Okay, so we don't have, you can see here, all these bipolar cells, rods and cones through here, and then our optic nerve has to come through here. So there's no rods or cones here. Okay, so this is where our blind spot is. In the middle of the optic nerve, through the middle of the optic disc, we have our artery and vein. Okay, that's what we see here, stretching out all these things here. These are the arteries and veins. Okay, and then off to the side, this is our macula and fovea. Okay, this is where all the cones are and no rods. Right. So we talked about the anterior chamber and the posterior chamber. Here we see the anterior, the cavities, anterior cavity and posterior cavity, and then that anterior cavity is broken up into chambers. Okay, the anterior chamber in front of the iris and the posterior chamber behind the iris. Okay, posterior chamber. The ciliary bodies here help produce the aqueous humor, and this kind of comes up, and you can see the arrows where it goes, and it comes around through the eye, and then it goes out through this little hole on the side, the sclerovenous sinus. Okay, so this is continually made and drained. Okay, so fluid. Okay, so it circulates through here, it's made, and then it drains out. Okay, the posterior chamber, this vitreous chamber, this is where the vitreous body is, this gelatinous substance. It's not replaced at all. Okay, we don't make more of it, we don't drain any of it. Okay, this is gelatinous, made of collagen and proteoglycans, and then the liquid part is the vitreous humor. So combine all that and you get that like jelly that we saw in the cow eye. So that's in our eyes. All right. Okay, so we'll talk about the lens and how we see. Okay, the lens, transparent biconcave flexible disc. Okay, it needs to be flexible so we can have focus the light. So we can put that focal distance and that focal point right on the fovea, the macula, so we can see the image clearly. Okay, so this bends and shapes based on the pulling of the suspensory ligaments. Okay, so if we need to see something close, it's going to relax and allow the lens to form more of like a circle. Okay, so it can bend that light more and have the focal distance still on the fovea. And then if it's further away, okay, it's going to thin out, so there's less of a refractive angle. So we can focus that focal point again on the fovea. Okay. So the lens itself is made up of cells. They don't have any organelles. Okay, they have crystallins. Crystallins are proteins that give the lens both the clarity and focusing power. Okay, and then a condition where the lens transparency decreases is called cataract. Okay, and then this could be from different drugs, could be injury, could be UV, or just aging causes the lens to become more cloudy. Okay. And then we can see with the picture here, those vocab words, the focal distance is from the lens to wherever all those points combine. It's focal distance, the focal point is where all of the point at which the light focuses. Okay. And then astigmatism is light passing through the cornea and lens is not refracted properly. Okay. So the visual image is distorted. Okay. So when you're trying to look at an image, this lens doesn't shape correctly to actually see what you need to see. Okay. So this adjustment of the eye is known as accommodation, so you can get a clear vision. Okay. The way this works is that when the ciliary muscles here contract, okay, this is the ciliary body, has the muscles here, and when it contracts, it pulls together. Okay. So this comes closer to this side, pulls together, contracts, and relaxes these ligaments. Okay. When these relax, the lens wants to be, if it was left alone, it would be in a ball. Okay, it would be a sphere. So these suspensory ligaments pull at it and keep it from being a ball. Okay. So when these suspensory ligaments are loosened, it pulls together and wants to become a ball. So it rounds out the lens when the ciliary muscles contract. Okay. When the ciliary muscles contract, when the ciliary muscles contract, they come together. So this comes towards the lens, this comes towards the lens, and it relaxes these. When we want to look at something far away for distance, okay, these ciliary muscles relax. So they move further away from each other, move further away, and tighten these suspensory ligaments. Okay. And we need to do that to alter the refractive angle here to give that focal point on the fovea so we can see. Okay. The visual acuity is how well we see, how well we can do this. We have 20/20 vision. This is how vision is measured. Okay, when we have those visual charts, we got to cover one eye, and we see how well we can see based on what row we can read. That's this. So what that means is 20/20. A person is able to see clearly an object 20 feet away. Okay, so an object that's 20 feet away appears clear at 20 feet away. Okay, when you have the denominator lower, okay, 20/15, a person can see an object at 20 feet with the detail as if it were at 15 feet. Okay, so they see better. Okay, they see more detail. Okay, when the bottom number is greater, a person like 20/30, a person sees an object that's at 20 feet as if it were 30 feet away. Okay, so it's less clear. Okay, so legally blind would be 220/200. Okay. Now, two other conditions here, scotoma and floater, abnormal blind spot. This is a permanent abnormality. Okay, this is where the optic nerve was damaged or the optic pathways visual pathways were damaged, and this is not getting correct. Okay, so this is called the scotoma, abnormal blind spot. Then we have floaters. Floaters are small spots that drift across the eye. So these are usually temporary. Okay, it's debris in the vitreous bodies. So usually those will be resorbed and it'll go away. All right, so emmetropia, that's normal vision. Myotropia is nearsightedness. So myotropia, this is where the curvature of the lens is too great. Okay, so this means that distant objects seem blurry. So you can only see close objects, nearsighted. And hyperopia is farsightedness. This is where the lens is too flat. So close objects seem blurry. All right. And then there's a good video on visual fields, visual paths, on one of the links that I have up on the page. But when an image comes in, it flips. Okay, so we have an image that's up high, it comes in and straight lines it down to the back of the retina, down low. And we have images that are down low, and it straight lines it up to the upper retina. Okay, same thing with right and left, those are switched. Okay, so they come in straight line to the opposite side. Okay. So the image is flipped, it's upside down, and then it's also backwards on the retina, the way its image is formed. Okay, so let's talk about the neurology of how this works, physiology of the cells here. So the visual pigments themselves are made up of rhodopsin. Rhodopsin is a molecule that's made up of opsin and retinol. Retinol is synthesized from vitamin A. Okay, that's why vitamin A is good for your eyes, because it is what makes up the rods and cones. Okay. when the cones are made up of the same thing, retinol and opsin, it's just a different form of opsin. Okay, so the cones themselves, we have 3 different kinds. We don't have a bunch of different colored, different cones that absorb a lot of different colors. We have 3, okay? So there's absorb at a different amount, and that gives us the color, okay? So you can see on this graph, and so if you were to only have the red cones absorbing the light, you only see red, okay? But then when you start to have green rods or green cones absorbing some of the light, you start to shift the color, okay? And it starts to blend together based on how much of each cone that you actually are stimulating, okay? There are a lot more red cones than the blue and green. And then the black line here is the rod, if the rods are stimulated. Okay, so this image here, it's in your book. They do a good job on the next slide with the spotlight on showing you how the light actually stimulates these. Okay, so next page. Okay, so these are the images that are in your book. It's a little bit harder to see on the PowerPoint here, but there's a spotlight in your book on page 586. That's really good. So it shows this resting darkness state. Okay, so we have this dark current that occurs. Okay, so there's no light here. There's no photons coming in, and we have a continual current where sodium is coming in, depolarizing the membranes, and then repolarizing here. Okay, so we have this continual current. This continual current causes neurotransmitter release onto the bipolar cells. Okay. When we have this continual release of neurotransmitters on the bipolar cells, it's kind of inhibitory to stimulating the ganglion cells. Okay, so we aren't stimulating the ganglion or the optic nerve when these neurotransmitters are flowing normally in this dark current. Okay. Now, when we have light coming in, we have a photon of light that comes in. Okay, here is our photon, comes in and it hits that retinol. Okay. When it hits the retinol, it changes from a cis form to a trans form, okay? When this is activated here, okay, when it goes to transform, it then creates PDE, okay, phosphodiesterase. This phosphodiesterase changes GMP to cyclic GMP. The cyclic GMP attaches to this sodium-gated channel, this gated sodium channel, and it closes it. Okay, so it shuts off this dark current that occurs when the photon comes in. Okay, when it shuts off these sodium channels, we have a change in voltage potential here, and we no longer have neurotransmitters being released, or the rate is changed of the neurotransmitter released, depending on how it's stimulated. Okay, so when we change the neurotransmitter release on that bipolar cell, that change in bipolar stimulation stimulates the ganglion. Okay. So that's how the light activates the rod or the cone and then transmits that signal to the optic nerve. When this current changes, okay, when that dark current shuts off, when that neurotransmitter release shuts off, that change in bipolar stimulation causes activation of the ganglion, which leads to the optic nerve. Okay. So there's a good picture and more description in your spotlight in your book. Here's another image. Okay, some vocab words, you don't have to worry too much about that, but one thing we'll talk about is bleaching. Okay, this is where, so here we have the photon coming in, changes that retinol to a trans form. Once we have that trans form, they separate. Okay, then when they separate, we need energy to change this retinol, trans retinol, to a cis retinol. Once it's back to a cis retinol, it can reassemble with opsin and form rhodopsin and is ready for stimulation again. Okay, so Once this is changed to a transform, it has to take time to separate, change back to a cis form, reassemble. Okay, so bleaching is a process where this rhodopsin is broken apart. Okay. And then you take time to actually combine them again to be able to be stimulated. Okay. So again, we have that photon coming in, changing the cis retinol to a trans retinol. Okay. This causes creation of PDE, and PDE changes GMP to cyclic GMP, which shuts off the sodium-gated channels. This changes the stimulation on the bipolar cells. Okay, so we have that dark current that exists when there's no photon activity. The sodium's coming in. Okay, when those are shut down, when the sodium channels are shut down, we no longer release this neurotransmitter. And when there's a change in this bipolar cell activation, that stimulates the ganglion. And the ganglion sends the signal down towards the optic nerve and down the visual pathways. Okay. So night blindness occurs when we have too little vitamin A. Okay, when you have too little vitamin A to synthesize this retinol, these visual pigments here, then we start noticing it at night because we have lower amounts of light. Okay, so we notice that our our rods are not being stimulated as much in lower light. You know, when we're bombarded with light during the day, we don't notice it as much, but we start to notice this vitamin A deficiency when at night when there's not a lot of light. Okay. And then we have dark adapted state. That's when the pigment is fully receptive to stimulation. And then light adapted state is when the state at which the bleaching, or the separation is balanced with the rate at which the visual pigment is assembled. Okay, so we have a balance between the cycle. Okay, you don't have to worry about those too much, but just know this little process. Know how the photon, what that actually does, changing the retinol, activating PDE and the cyclic GMP, that kind of stuff. Okay, so know that pathway, know the order of what happens with that. Okay. All right, color blindness, inability to distinguish certain colors. Okay, the object appears to have a particular color when it reflects photons from one portion of the visible spectrum and absorbs the rest. Color discrimination takes place through the integration of information arriving from the three types of cones. So we already talked about that. So when you have a different amount of stimulation from the blue, green, and red, you create a different color. Okay, so that's what that's describing. Visual information ends up in the visual cortex with the occipital lobe. Okay, we'll look at that in a second. And then the nervous impulse begins at the photoreceptor, and then synapses twice, once at the bipolar cell and the ganglion cell. Okay, that's what we have here. We have the photoreceptors, synapses with the bipolar cell, and synapses with the ganglion cell. And this takes it to the optic tract. Okay. So this little picture shows our receptive field. Okay, so each ganglion may accept many different bipolar cells. Okay. So we could have thousands of different photoreceptors activating bipolar cells, activating the ganglion. Okay, so the ganglion is in charge of all of this receptive field. All of these photoreceptors in this part of the retina this ganglion is responsible for. Okay. All right. So M cells are magna cells are large ganglion cells that monitor rods. And then P cells are the smaller cells and more numerous ganglions that monitor cones. Okay. Okay, so here's the visual field. Okay. We see that, like we talked about a little bit earlier, okay, the things in your left visual field attach to the right retina here. Okay, it comes straight across onto the right retina. The right visual field comes across to the left retina. Okay. So now we have images on the retina, okay, that are flipped. Okay. The nasoretinal images, okay, so this is your nose, so nasoretinal images, those cross, okay, and both of the nasoretinal images cross and go to the opposite side. The temporal retinal images stay on the same side. They go back to the lateral geniculate nucleus where they synapse, and then they head through the projecting fibers to the occipital lobe. Okay. So that's the pathway for binocular vision. Depth perception, you need that is produced because you have two eyes. Okay? You're able to determine depth with binocular vision, interpreting a three-dimensional relationship among objects. Suprachiasmatic nucleus and the pineal gland receive information as well. Okay, that's here, suprachiasmatic nucleus. Okay. And then we have pineal gland is a little bit further. Okay, those receive information to help establish a circadian rhythm. Okay, so this is what's stimulated when you have that light coming in. Helps establish that circadian rhythm, which is why you shouldn't be looking at a backlit screen real late at night. So hopefully you're doing this in the middle of the day. But when you're stimulating that at night, when everything else is dark, you're stimulating the suprachiasmatic nucleus and the pineal gland so that you're altering your circadian rhythm, because your circadian rhythm thinks, your body thinks, hey, there's a lot of light out there, it must be daytime. So it's going to affect your hormones and different things like that. Okay, so this is the end of that. That's the ear. So we're going to start that on another PowerPoint. Hopefully I hit everything well enough for you guys. Look over that. If you have questions, let me know. Send me an email, text, and let me know. And we'll see you on the next video on the ear.